Okay, let me start my talk. My name is Yongjung Kim. I'm a Sejong Science Fellow at Gyeongbuk National University. First of all, thank for inviting me. Thank for giving me a chance for this kind of contribute talk in Gemini Science meeting after the last meeting in 2018. And today I'll give a talk about the searching for highly faint quasars with the infrared medium deep survey shuttle in IMS. And I'm currently working with Professor Myung-shin Lim at Seoul National University and other guys related to the IMS project. Thanks to the previous speakers, we already know that why the quasars are important, especially in the early universe. And so I just briefly review the basic concepts here. This figure shows that the ionization state of the hydrogens along the cosmic time, and after the recombination, most of the hydrogens remains in neutral, but at around the redshift 6 something, after there's some stars and galaxies born, nowadays all the hydrogens are in the fully ionized. Fully ionized. And this figure shows the neutral fraction of the hydrogens along the cosmic time, and as you can see, such a transition have occurred around within a very short time around the redshift 6 and 7. This means that most of the hydrogens are already fully ionized at redshift lower than 6. And here the key question is that which object can keep this ionized hydrogen after the part of the reionization. Quasars are very bright, even in UV, so they are expected to provide enough UV photons to hit the ionized state of the hydrogen in the universe. But the problem is that the right figure shows the UV emissivity of quasars, but as you can see in this figure, there are a lot of scatters between the studies to which they drive some UV emissivity. This is because of the lack of the faint quasars. The left figure shows the differential UV emissivity as a function of the magnitude, and as you can see here, they peak around the -23 absolute magnitude. But the problem was that just a few years ago, there are not many quasars in this magnitude range. So this gives some lot of uncertainty when we determine the number density in this magnitude range, giving some lot of scatters in the UV emissivity. So it was not easy to constrain the quasar's role in the ionizing, giving this kind of ionizing process. So we targeted to find some such faint quasars with the infrared medium wave survey, the shuttle IMS. IMS is a near-infrared imaging survey, which using some wide field camera on the UCURT, and it covers over 100 square degree area, and in Y and J band, and J band depth reaches down to 23 of planetary magnitude, is relatively deeper than the all sky surveys. And combining this with the CFST-11 survey, CFST-LS optical data, we have performed some highly quasar survey as faint as the -23 absolute magnitude at redshift 5 and 6. As the previous speakers already mentioned, the high quasars have a very steep and very clear line of break, as you can see in the left figure. But so this gives a very red broadband colors, and such a broadband colors are usually widely used for finding some high-redshift quasars in the previous studies. We also initially select the quasar candidates using the broadband colors. As you can see in the right two figures, these figures show the broadband color diagram at redshift 5 and 6. And as you can see, the quasars are located at the bottom right of this diagram. We set some selection criteria, color selection criteria, and we initially select the 69 and 25 quasar candidates at redshift 5 and 6 respectively. The problem is that the success rate of the quasar identification with only broadband is very low. For example, only so as the student said, there is about the 30% something at ratio 5 and 6, something like that. So here we introduced a new method to improve the selection. The first idea was that the medium, including the medium band follow observation. Medium band here is here has a bandwidth of the 500 Armstrong, and this gives a very more detailed, giving us more detailed photometry. For example, this figure shows the broadband and medium band photometry of the quasar and dwarf stars. As you can see here, the broadband photometry of these two targets are very similar to each other, but when you see the medium band, we can easily distinguish it from the quasars from the interlocal like dwarf stars with this kind of color system. So we adopted the color selection criteria in medium band, and as you can see here, this is the medium band color criteria or color diagram that we used, and you select like this kind of objects from our targets. Among the 69 quasar candidates at ratio 5, 33 satisfied our criterion, so we take this as our plausible candidates. In the case of the ratio 6 quasars, we introduced another method that using the information criterion. Information criterion usually prioritize the models for a given data set. And here we use the corrected archaic information criterion, shortly AICC, because AICC is known to be very powerful for the small data set. So we apply this AICC to the iris quasar and low type star models, and calculate and set some criteria to find some good samples. And 7 out of 25 candidates were selected as plausible candidates. Now we have our plausible candidates at ratio 5 and 6. So we have performed some spectroscopy to identify their true nature. Most of them are very faint as about the 23 apparent magnitude, so it is not easy to observe them with a normal telescope. So we need a very large telescope, like so we use the GMOS on Gemini and IMS on Magellan and DBSP on Palomar 200-inch telescopes. And as you can see here, it's remarkable that most of 20 of them are identified by the GMOS on Gemini. And so here I greatly thank for Cajun Design School, Kathy, and Gemini Observatory for this kind of achievement. So the right figure shows our 24 IMS quasars as faint as the -23 magnitude. And with this quasars, we checked our method with the method. First, we checked some medium metafollow method. And it's amazing that among the 33 medium band selected candidates, 32 are identified as ratio 5 quasars, including the previously known ones. And unfortunately, there are some 5 quasars that are not selected by our criteria, but this is due to the medium band imaging depths. So they deserve to be missed. And in natural, the inclusion of the medium band critically highly improved the determination of the photometric redshift or only a case of the 1 or 2%. And this gives the prospects for the future medium band survey for all sky at 7 years like that. And the second one is the AICC selection. And among the 7 AICC selected candidates, we obtained all the spectra of the band, including some known ones, and 5 of them are identified as ratio 6 quasars. And this is relatively higher than the 30% that I mentioned before. But for the non-selected candidates, we cross-check them with the HSC optical data, which is 1 magnitude deeper than our data. Among the 25 broadband color selected candidates, 14 candidates are also covered by the HSC, and there are 2 quasars satisfying the AICC selection. It is interesting that both of them have a very red colors, both in our data and HSC, as you can see here. The right figure shows the color. the right figure shows the blue band color diagram, and these two have a very red colors. Even we check even on the HS data. Note that this solid line is the expected colors of the quasars. So and they are consistent with the expectation. On the other end, the other 12 candidates that are not selected by the AISS method have a red colors in our data, but with a more deeper HS data, they move toward to the stellar locus like that. This means that they are not likely to be Irish quasars. So this suggests that our method is very effective for searching the quasars at the survey detection limits, considering that most of them are very faint ones, having some 23 apparent magnitude like that. So with this data, we now wanted to estimate the number density or quasar linear function at verse 5 and 6. This figure and this slide shows some survey completeness and selection functions, and this means that how the quasar models can be selected with our data and our selection method. We calculate this survey completeness to finally estimate the number density. I just skip the details here. So with the survey completeness and the selection functions and our discovered quasars, including the quasars here, we derive the quasar luminous functions at ratio 5 and 6. We estimate the bind QLF and the parametric QLF, and this figure shows that the results at ratio 5 and ratio 6 on the right. And our results are shown as the red symbols, like the red circles on the left figure with some red solid lines, and also red circles on the right figure. And as you can see here, our results are show that in this faint magnitude range, they have a very faint, they are very flat, faint and slope like this. And this is much lower than the previous results from the surveys that covering only the less than the 10 square degree area. We also checked there's some partial. We also checked the partial number densities from our surveys and concluded that such a high number density from the previous works are due to the small survey area, and they might overestimate it, might be overestimated. And so this note that our results are in line with the results from the wide field surveys. And using this number densities, we now calculate the UV emissivity of quasars, whether to see the quasar role in the ionizing process. We assume the very simple quasar UV spectral shade, and using the quasar linear function, we calculated the UV emissivity. As I mentioned in the introduction, there are a lot of scatters in the UV emissivity on the cosmic time, and our results are shown as these red points. But if we focus on the data from the wide field survey, you can see that all the results are in line with the model, shown as some lines that the UV emissivity decreases as redshift goes higher, and this goes higher, yeah. So we conclude that such a trend is our results are in line with this trend. And another previous studies derived the photon density required to keep the ionized state of the hydrogen, and from various methods. But here I show the two methods which are shown as the gray squares and gray shaded regions. Comparing this with our results, our results show that the quasars can only provide 10% of the required photons at ratio 5 and less than 3% at ratio 6. So we concluded that the quasars alone couldn't provide enough UV photons to keep all the hydrogen the ionized state of the ionized hydrogen after the epoch of the reionization. And according to the another studies, maybe the star-forming galaxies may play a key role for this kind of process. So here's a summary of my talk, and thank you for your listening. Yeah, and please feel free to ask any questions.
Thank you. Is there any questions from audience? Flag. Any questions? Okay, so then you said that Quasars is not the main driver for the ionizing the AGM.
Yep.
Then
yeah, they are not up to yeah, their number density is not up to give some enough photons. And
then what source are the main contributor to this ionizing?
Yeah, actually, other studies say that the star-forming galaxies may play a key role to provide the UV photons, but the problem is that the escape fraction of the Lyman continuum photons, because to satisfy the criterion that I mentioned here, that the gray lines here, the star-forming galaxies should have some very high escape fraction, like some 20%, something like that, but it's very, very high compared to nearby galaxies that having some 33%, 1%, something like that. So it's still not solved, but yeah, but we need to study more about that to solve this question.
Thank you. Any other questions? Okay, then thanks Youngjeong again.
Thanks.